Push the buttons one at a time in order and count each push. That total is your answer. You get to choose how the letters are split up among keys 2 through 9, with each key getting its own distinct set of letters. And the trick is finding the split that adds up to the fewest total pushes for spelling out the word. Take a advanced level. This is an assignment problem in disguise. Minimize sum of cost times weight over a free bijection from letters to key slots. Fix T9 is one arbitrary assignment. We are optimizing over all of them. Keep that framing. It's the whole problem. You already know this as Huffman's matching slopes argument. Minimize sum of cost times weight by pairing the smallest costs with the largest weights. Same rearrangement inequality that underlies optimal prefix codes and priority scheduling. Recognizing the shape early tells you the answer is greedy before you've written a line. Degenerate case, 5 distinct letters, all weight 1, all under the 8 key threshold, so the assignment is irrelevant. Every valid bijection gives 5. Useful as a sanity check that your solution doesn't do unnecessary work when the ladder never engages. No heap needed here. That's worth noting explicitly. A heap earns its cost when you need incremental top k or a changing weight set. Here the weight set is static and bounded by 26, so a single O2D6 log 26 sort dominates any heap-based streaming approach. Frequency count, 1 descending sort, 1 linear pass with integer division. That's the entire solution space explored. The binding constraint isn't n up to 100,000. That just sets the counting pass to own. The alphabet cap of 26 is what makes the assignment step trivial. Cost per letter is bounded by 0.268,000 POSO. There is no asymptotic tension to exploit, only the ranking logic. Worth stating precisely. The real T9 layout is a feasible, but generally suboptimal point in the same solution space we are searching. It's a useful adversarial example if you want to construct a word where naive fixed mapping cost diverges arbitrarily from optimal. Good interview follow-up to pose yourself. Sort weights descending, fill cost 1 across all 8 keys first, then cost 2, and so on. This is just Huffman style, greedy bucketing with a fixed branching factor of 8 instead of 2. The reason it's correct isn't intuition, it's the exchange argument on the next slide. Make sure you can produce that proof on demand. This is the full correctness proof, not just intuition. Take any optimal assignment. If some pair freak key I freak chi has cost t I cost chi, swapping their slots changes total cost by freak key. Freak chi cost chi, cost g, cost g, cost gt, freak jigs, cost ti, le. Strictly negative unless freak chi. So any assignment not sorted by frequency admits a strict improvement or a tie, meaning the sorted assignment is optimal. This is a textbook exchange argument, same proof structure as interval scheduling and Huffman coding, cited by name if asked to JGD. Generalize this immediately for k keys and an alphabet of size m. Cost rank, ring cost, king cob, rank cost, king cob. Was 1 and max cost is king cob. Swap in 26 keys or a different alphabet and the formula doesn't change, only the constants do. That generalization is a natural interview follow-up, so have the closed form ready. 9 distinct letters, sorted descending. This is also the minimal example where the greedy answer diverges from the naive, use fixed T9's answer, worth constructing on a whiteboard if asked to argue optimality without the formal proof. Note what we are discarding. Which letter had which frequency doesn't matter, only the multiset of frequencies. That's why we sort freak.values and never touch the keys again. The problem reduces entirely to an unlabeled weight sequence. This closed form loop is exactly the sorted assignment optimum from the exchange argument, expressed as a weighted sum. No heap, no explicit key simulation. Cost per rank is a pure function of rank, so it collapses to one pass. Place it once to confirm the off by 1 is right. Rank 7 8 letters till floor divides to 0. Rank 8 9th letter is the first to hit 1. If you ever get this wrong under pressure, it's almost always an off by 1 at the rank key. Boundary. Check it against Coit exactly here. Quick check. Before computing it, ask yourself, does the tie between the two frequency 2 letters affect the answer at all? If not, why not? Given the exchange argument only cares about relative order among unequal weights, right? Ties are interchangeable in the exchange argument since swapping equal weights changes cost by 0. Any tie-breaking rule in sorted gives an equally optimal answer, which is why the algorithm doesn't need a stable or deterministic tiebreak to be correct. The subtler failure mode at this level, someone reaches for a heap or a full assignment. Problem solver Hungarian algorithm out of habit, missing that the cost structure is separable and monotonic in rank, which is exactly what makes greedy probably optimal here and turns an own log n or worse general solution into own. Recognizing when the general tool is overkill is actual skill being tested. Formally, on to count, O26 log 26 to sort, which is on since the alphabet is fixed, so total is on. Bucket sort by frequency counts up to n, so when buckets removes even that constant. But it's not asymptotically better here. Only worth it if the alphabet weren't bounded by a small constant, e.g. Unicode scale symbol sets. The sharper edge case to probe, what if the word has exactly 8 distinct letters versus 9? Does the discontinuity in marginal cost? And it's where a buggy boundary condition would actually surface. Also worth checking mentally, the formula degrades gracefully to cost 1 for the KMA 8 distinct letter case without any special casing, which is a signal the solution is genuinely general rather than patched for small inputs. Generalizations worth having ready. K keys instead of 8, change the divisor. Non-uniform cost per press instead of linear rank breaks the simple floor division, but the exchange argument and greedy by weight still hold as long as cost is non-decreasing in rank or a hard constraint on max letters per key. Rather than unlimited then it becomes a genuine bin packing flavored assignment, no longer solvable by a single sort. The sibling problem, word 1 ranking by first appearance instead of frequency, is a good check that you actually K keys instead of frequency is a good check that you actually understand why frequency non-decreasing. Quick one before you go. We sort letters by frequency before handing out keys. Why does the greedy sort actually minimize total pushes? Pause and think it through. Think about what each slot on the key actually costs you. Every key has a 1 press slot, a 2 press slot, and a 3 press slot. So you want your most used letters sitting in the cheapest slots, and sorting by frequency guarantees exactly that. Second one, if a word only has 5 distinct letters, does sorting by frequency even change the answer? Take a second and guess. Count how many keys 5 letters actually fills. Nope. With only 5 distinct letters, every single one lands in a 1 press slot no matter the order, since you've got 8 keys to spread across. Frequency sorting only starts mattering once you cross 8 distinct letters.